Welcome to Hartman Math. Before we get to solving exponential and logarithmic equations, let's review some log properties. Go ahead and approximate each log. Given these facts that we have log unknown base b of 3, 5, 14, and so on, use those to see if we can get some approximations for these two problems. Pause here and go ahead and work it out. All right, number one. Kind of see what we're dealing with here. We got the 3, we got the 14. It's division, so that's quotient property. Let's split this up. Log base b of 3 minus log base b of 14. And then we can replace and do the subtraction. And we would get about a negative 1.759. And then for number 2, 75. Well, let's see. 75, I don't think it has anything to do with the 14, but maybe the 3 and the 5. We thought of that as 3 times 25. So split that up with product. And then 25 is 5 squared. And there's more than one way to do this. So 2 times log base b of 5. So log base b of 3 plus 2 of the log base b of 5s. And we would get about 4.931. This is lesson 3.4 Exponential and Logarithmic Equations. Here's some strategies. Rewrite in a form that allows use of the one-to-one properties. Rewrite an exponential equation in log form. Or vice versa, rewrite a log equation in exponential form. All right, example number 2. E to the power equals e to the power. So we can use the one-to-one property, which had said e to the power of, if e to the power of x equals e to the power of y, then x equals y. So in this case, exponent has to equal exponent, so we can start that way. That's the one-to-one property. Now, as a quadratic equation, let's get it equal to 0. I don't particularly care for the negative x squared. I would like a positive x squared, so I'm going to add x squared to both sides. And that does make the left side 0. We can then factor that. From those factors, we get x equals negative 3, x equals negative 2. Example 2, part B, solve. Let's see if we can go ahead and isolate. So get rid of the 4. Let's divide both sides by 4. And then no common base, so I don't think we're going to be able to use the one-to-one property, but we could rewrite this by moving the base, rewrite it as a log equation, x equals log base 3 of 16. And that's our exact. And then approximate to 3 decimal places. This is where we would use the change of base formula and do log 16 divided by log 3. Or if your graphing calculator allows to directly input it like that, that's fine too. We get about x to be 2.524 approximately. All right, part C, let's do something similar. Let's add 3 to both sides. Let's divide by 7, but not round that. Leave it exact. And then if we're going to rewrite this from exponential form into log form, we would move the base. The base is e. So the right side becomes log base e of, log base e is just natural log. So maybe we could just say x plus 2 equals the natural log of, and then we can subtract 2 both sides. So there's our exact answer. Let's make sure you carefully type that into your calculator. We should get x is about negative 0.810. Example 4, part A. A little bit more extreme, same idea though. We could subtract 1 both sides. Divide by 7 both sides. Rewrite this from exponential form to log form by moving the base. Add 4 to both sides. Divide by 3 on both sides. So t is equal to log base 5 of 4/7 plus 4 all over 3. And then it seems like a pretty tricky one to do on the calculator. We might want to take our time, do this, add 4, hit equals, divide by 3, hit equals again. That's one way. Or you could put parentheses on top of all this. Either way, you should be getting about 1.217. Example number 4. Ooh, this looks a little different. I wonder why that's the case. Because everything we've done thus far has been sort of an extension of things that you've learned from maybe a previous course, Math 3, in regards to logarithms, exponential functions, even the equation stuff. But this is definitely next level. This is a true pre-calculus, maybe even honors pre-calculus problem, where we have different bases, and clearly they don't share the same base. Because if this had been a base of 4, I don't think we have an issue. Because we could then just say, I would like both sides to be powers of 2, and then we could use the one-to-one property. But we don't have that option here. So, what are we going to do? Well, the idea is we have our x's up here in the exponents, and if it was just one of them, any of the previous strategies that we've been using would be okay. Now we have it for both, so that's our issue. So we want to bring these down, and the way we're going to do that is using the power property of logarithms. We can take these exponents and bring them down using the power property. Well, we then need logarithms. So we're going to need to take a logarithm on both sides. I don't suggest choosing one of these. I suggest using one of our standard or common bases, either base 10 or base e. We're going to go base 10. So start there. Take a common logarithm on both sides. Then we can use the power property. Now, when we do that, this whole thing has to be multiplied, so it's got to be in parentheses. And now it becomes an algebra problem. Do not get distracted by log 3. It's just a number. So if this was 14, would you know what to do? If this was 7, would you know what to do at that point? We're just going to do some algebra. We're going to distribute and distribute, because this is just a number. And then our goal is to solve for x, so we want to get all the x's on one side, and then we'll just get everything else to the other side. So to minimize the number of negatives, I'm going to say, let's get the x's to this side, and we'll move this back over here. So we're going to subtract 2x times log 2. We're going to add 2 times log of 3 to both sides. Again, think algebra. How do I get this just to be 1x? What can we do? Factor. Factor out an x. And then over here, I think at some point we're going to maybe start kind of figuring out what this is by some of our properties. Like I could take the 2 and move it up top, which is the same thing here. So we factored out the x. This is 2 log 2. The 2 goes up, so it's log of 2 squared. That's 4. This is log of 3 squared using the power property, so that's log 9. Now we can condense these to one single log, quotient property. One single log, product property. Divide both sides by log of 3/4. So x equals log 18 divided by log of 3/4, or we could use the change of base when we have log divided by log. That's log of, there's the base, there's the argument. So I like it this way, log base 3/4 of 18. It did not mention approximating, so we're just going to leave it exact. All right, checkpoints A and B. Pause here as you work through both. Part A, let's divide both sides by 4. Then we can rewrite it as log, and since it's base E, we're talking about natural log. We'll can divide by 2 or multiply by 1/2 either way. So there's our exact answer. Part B, I think we could factor this. E to the x minus 3, e to the x minus 6, e to the x equals 3, e to the x equals 6. Rewrite those. X equals log base e of 3, and that's natural log. Go. So for log equations, we've been looking at exponential equations, but for log equations, we're going to kind of use similar strategies. But because log functions have limited domains, it means you always have to check your answers. All right, so I think we can start with a pretty easy one here. We could use the 1-to-1 property. Log base 7 of equals log base 7 of. So argument has to equal argument. Solve for x. Before we box that, we probably should check it. So if we substitute in, we would get 2 times 2 plus 3 is 7. Log base 7 of 7 equals log base 7 of 7. That's definitely true. If you substitute in, you get something like log base 7 of 0 equals log base 7 of 0. It sounds true, but it's not, because there's no such thing as log base 7 of 0. Remember, the argument, not the solution, argument has to be positive. Okay, it can't be negative, can't be 0. Can't take the log of a negative number or 0. All right, part B. Log base 2 of 3x equals 4. Let's rewrite this out of log form. Let's move the base to the other side. Not the greatest example, because even if we did it wrong, I think we get the right answer. But this should be 2 to the 4th power. 3x equals 2 to the 4th power, which is 16. So x equals 16 divided by 3. Right, part C, log of x squared is equal to 2. Well, what's the base? If we're going to rewrite this into the other form, we need to know the base. What's the base here? It's base 10. It's the common log. So it's base 10, so we're going to rewrite it, move it over 10 to the 2nd power. X squared equals 10 squared, which is 100. So square root both sides. Plus or minus, x equals plus or minus 10. All right, do both of those work? What about 10? 10 squared is 100. Log of 100 is 2. Yes. Negative 10. I'm worried about this one. Negative 10. If we square negative 10, we're still going to get 100. The log of 100 is 2. So actually both of them are correct. Make sure we check our answers. Example 6, part D. There's a lot of logs in this one. So my worry over here is the left side with log plus log. So I'm pretty sure we're going to need to use log properties to condense. Log plus log. So that's the product property. So one single natural log, this times this. And then once we've done that, we have log equals log. So now we can use the 1-to-1 property. Argument has to equal argument. If we only had one log, we would need to rewrite by moving the base. But we have log equals log, so that's just the 1-to-1 property. This product equals x squared. It's quadratic, let's get it equal to 0. It's going to factor. We get potential solutions of 1 and 6. All right, let's check them out. Let's try the 1. Natural log of 1 minus 2. That's not going to work. That's negative. You can't take the natural log of a negative number. Throw that one out. How about the natural log of 6 minus 2? The natural log of 4. We can take natural log of 4. And here we would get natural log of 9. So if we think about that, natural log of 4 plus the natural log of 9, product property would be the natural log of 4 times 9, 36. And then if we think about it this way, 6 squared, that's a natural log of 36 also. That definitely works. There's our solution. What we're mainly checking for is no domain violations. Example 6, part E. Solve. So we've got log minus log. I mean, we could think of adding it over, but the 2 is going to be a problem. It's going to mean that we wouldn't be able to use the 1-to-1 property. would have to be log equals log. So the 2 kind of ruins that. If it was a 0, I think we could just add this over and use the 1-to-1 property. But without that happening, I think we're going to go minus, use the quotient property, log, numerator, denominator. And then let's rewrite it by moving the base. Again, we're talking about base 10. So move that over, it becomes 10 to the 2nd power. That's 100. Undo the division, multiply both sides by 12 plus root x. And it looks tricky. It's a bit of a quadratic problem if we understand that if we think of that if we square root x, we're going to get x. So it is a quadratic style problem. So we probably want to get it equal to 0. Okay? Or we can kind of really turn it into a quadratic problem. Do what's called a u substitution. Say u is this, and then that means if I square both sides, that x becomes u squared. So for u squared, we replace the root x with u. And then we can get it equal to 0. We could also divide everything by 4. And maybe quadratic formula from there. U equals, by the quadratic formula, 25 plus 5 square root 73 all over 2. Remember, what are we solving for? We're solving for x. I didn't choose the minus one, remember, because quadratic formula had plus or minus. But I believe the minus is going to give us a negative. And from this, u can't be negative. U is the square root of some number x. It's not going to be able to be negative. So we eliminated the negative there. So now we want to get x. So how would we get x from this? Well, if I square both sides, x would be u squared. So I just got to square this, and we've got our solution. So x is that squared. Checkpoint. Log base 4. Log base 2 here. Pause here as you work through both. All right, so we're going to rewrite this one. 4 to the 1/2 power means the square root of 4. And that's 2. You multiply both sides by x minus 1. Subtract the 2x, you get negative x equals negative 2, so x equals 2. Quick check on that. Looks okay. Over here, we can do the product property, log base 2 of x times x plus 5. We're going to rewrite by moving the base, so it's 2 to the 3rd power, that's 8. From there, we're going to get it equal to 0. Quadratic formula. Once again, in this case, because we're right here, x is not allowed to be negative. So the minus one, that would have definitely turned out to be negative. This one should be okay. Negative 5 plus the square root of 57 over 2 is positive. So we're okay there. That's our solution. Example number 10, doubling an investment. You have deposited some money in an account that pays this interest compounded continuously. How long will it take your money to double? Since we're talking about continuously, that's talking about A equals P times E to the RT. We don't know how much money we're starting with, so let's say we're starting with P, starting amount. And if we're going to double it, how much money are we ending with? 2P. And then we could divide both sides by 2. Divide both sides by P. And we're here. And we can rewrite this from log form, from exponential form to log form by moving the base. So if we're talking about log base E of 2, that's the natural log of 2. Divide by 0.0675, we've got our T. 10.3 years. finish with example, simplify. E to the natural log 4 minus 3x. So we have from our log properties, actually not from the 3.3 lesson, but from the 3.2 lesson, from those log properties, we have this being an inverse property. E to the power of natural log, those are inverses and they're going to cancel each other out. We're going to get 4 minus 3x. But we have to think in terms of what is 4 minus 3x allowed to be. Because the first thing that happens to it is that we take the natural log. Only allowed to take the natural log of positive numbers. So, we get 4 minus 3x under the condition that x is, well, 4 minus 3x has to be greater than 0. So if we solve that, x has to be less than 4/3 in this expression. Otherwise, if it's not, we're taking the natural log of something we can't take the natural log of, and we wouldn't get a response. So careful on those with the log on top here as part of the exponent, as that kind of dominates the domain part to that. That's it for today. I'll see you next time.